The prevailing theory, known as the Nebular Hypothesis, suggests that Earth formed approximately 4.6 billion years ago from a giant cloud of gas and dust called the solar nebula. This nebula consisted of remnants from previous generations of stars and was triggered to collapse under the influence of gravity, possibly due to the explosion of a nearby supernova. As the cloud collapsed, it started to spin and flatten into a rotating disk. The central region, called the proto-Sun or proto-Sun, grew hotter and denser, eventually becoming the Sun. The remaining material in the disk began to clump together due to gravity, forming smaller protoplanets and planetesimals. Over time, the protoplanets collided and merged, gradually forming larger bodies. These collisions were intense and frequent, leading to the release of enormous amounts of energy and heat. Eventually, one such collision between a Mars-sized object called Theia and Earth occurred, resulting in the ejection of debris that later formed the Moon. As Earth continued to accrete material, it underwent significant differentiation. Heavier elements sank toward the center, forming the core, while lighter elements and compounds formed the mantle and crust. The heat generated from the collisions and the decay of radioactive isotopes further contributed to the melting and differentiation of Earth's interior. The early Earth was a hostile place, experiencing intense volcanic activity, frequent meteorite impacts, and a thick toxic atmosphere dominated by gases such as methane, ammonia, and water vapor. Over time, volcanic outgassing and other geological processes gradually transformed the atmosphere, leading to the development of the current composition, dominated by nitrogen, oxygen, and traces of other gases. As the Earth cooled and solidified, liquid water could exist on its surface. This marked a crucial turning point for the emergence of life. The precise origins of life on Earth remain uncertain, but it is thought to have originated in the form of simple, self-replicating molecules that eventually evolved into the diverse array of life forms we see today. Studying the origin of Earth is an ongoing endeavor, with scientists continually refining their understanding through a combination of theoretical models, computer simulations, laboratory experiments, and space missions. By exploring our planet's origins, we gain valuable insights into the broader processes that shape not only Earth, but also other CE